So elasticity is actually an extension of what we have discussed before, the Hooke's law. It's also a natural extension of the rigid body discussions we have had for quite a while. So remember back when we didn't really understand rigid body, we just had point masses, right? Point masses don't have shapes, they don't rotate, right? So that was back before rigid bodies were introduced. And then after rigid bodies were introduced, we're actually we had to consider rotation, right? Rotations besides translations. So what if a rigid body is not enough to describe the physical situation? Then the body cannot be rigid anymore. It has to be compressible. So elasticity comes after that. So let's review what we had before in terms of elasticity. Hooke's law. Hooke's law is for a spring or any spring-like object. You can stretch, compress, and Hooke's law tells you how much the force of the spring is proportional to the k, the spring constant, and then delta x. So if you use a vector displacement, then you can also use the vector force and put a negative to indicate that if you stretch to the right, the Hooke's law, the restoring force pulls you toward the left, or the other way around. If you say compresses to the left, it pushes you toward the right. So this Hooke's law is applicable to situations where you have, for example, a bar. So let's discuss tensile stress and the strain. This is a slight extension of Hooke's law. So we have an object that is very elongated. It has a length L, and it's fixed at one end. The other end is free to move, so you stretch it with a force. This is the force, and the result is it has been stretched for a little distance. And this little distance is delta L. So that's a result. And we also have some knowledge of the area of this elongated shape. So area is A. You can imagine applying the same force with a much thicker bar will result in a much less stretch of this delta L. So the force over the area is important. So if you have a larger cross-sectional area, you should apply a proportionally large force to see the same amount of stretch. So we define stress as force over area. And force is in newtons and area is in meters. So Newton per square meter. And this unit is also called Pascal. So that's the same as, CAL. So that's the same as pressure atmospheric pressure in liquid. So that's the same exact unit, stress. And then strain is defined as not delta L, right? We had the delta X for stretching a spring. So this strain is defined as delta L over the overall L. So this gives you an idea of the percentage change in length. And you can imagine if you have a longer length, you may have the same proportional change, but you'll have a larger absolute change in L. So the strain, it has no unit because the change in length and the length are both in length unit, meters or whatever unit. So this is dimensionless. Okay, and to link the stress and strain together, we have a factor just like we have in Hooke's law. There's a this spring constant. So we have stress equals y strain, and this y is called a modulus. named after Young. So it's Young's modulus. And this can be generalized into a more general form is stress equals modulus times strain, because there can be different types of stress and strain situation. Just to give you an idea how large this Young's modulus is, so Young's modulus for aluminum, for example, is fairly large. This value is 7.0 times 10 to the 10th power. It has the same unit as the stress because strain is dimensionless. So this is Pascal. And it probably helps to emphasize that the force here is a perpendicular force, perpendicular to the area. So this force F perpendicular is perpendicular to the area, the cross-sectional area. You're actually just purely stretching it. So that's okay. Back to the Young's modulus. Young's modulus for something that's a little more stretchy rubber, silicone rubber, is 0.001 times 10 to the 10th power Pascal. So this is the same exact base, 10 to the 10th power, 10 to the 10th power. Value is very big, but this is a thousandth of 1. So 7 thousandths more stretchable. And that's why we usually don't see aluminum stretch at all, or actually exhibit string at all. But we do see rubber stretch up, right? Exhibit some delta L. It's just it does do it. It just does it very slightly. So this is tensile stress, and there's another type of stress and strain is if you take an object, a volume, and try to press it and reduce its volume. For example, if you maybe take a stress relief ball and try to squeeze it, make it smaller, and it tries to bounce back. So this is considered a bulk stress. So let's start on the right side. If you squeeze a stress relief ball. So say we have a box. Box is easier. And we apply forces all over in order to compress it, right? So something like this. Okay, so I just made sure I drew, let's see, 1, 2, 3, 4, 5, 6, all 6 sizes. So we have a force per area. So force per area applied. And this happens to be just pressure. We can apply pressure. So stress, again, is this force over area. So we're assuming that the force is perpendicular again. So we can certainly say this here. Just say perpendicular. So first perpendicular is stress, and it's in Newton per meters again, so it's in Pascal, PA. And then the strain is we have a change in volume. So after this, it's difficult to draw, but I'll try. So I'll try and draw a smaller sphere. So this sphere has shrunken down. So there's a change of volume, and then there's the overall volume. So this is again dimensionless quantity. So to relate the two, we just use this general formula: stress equals modulus times strain. So we have force perpendicular over area equals bulk modulus times change of volume over volume. So this is bulk modulus. And bulk modulus and the Young's modulus are very similar. So I'll give you an example. For aluminum again. Oops. For aluminum, and the bulk modulus is 7.5 times 10 to the 10th power pascals. So very similar to the Young's modulus. And for bulk modulus of rubber, it has a value of 0.2 times 10 to the 10th power. So it's a bit difficult to actually to compress the volume of rubber, although it's easy to stretch it, right? The stretching it kind of ignores the fact that this width, the area actually shrinks a small amount in order to accommodate for the stretch, so that the total volume of the stretched rubber band may not be as big as you would imagine with a constant area, cross-sectional area as maintained, right? So now we have bulk and the tensile. We have a third one. This one is a shear, stress, and strain. So let's put it down here. Oops, that doesn't look good. So shear, stress, and strain. What happens over here is, let's draw this maybe on the right side so we have enough space. So we have an object that's also elongated. Instead of applying force to compress or stretch it, we apply a shear force this direction. So this is an F parallel to the surface. So this F parallel causes the object to shear away. Let's use a ruler for that. So the object has sheared. And the amount of displacement of this end is x, and the overall height of the object is h. So to describe this this stress and strain, I have stress is equal to this F parallel over the total area, and the same as Pascal, same unit, and strain, again a dimensionless quantity. Now we have an x over h, right? Okay, dimensionless. And to relate them, we have stress equals modulus times strain. So stress equals shear modulus times strain. And as you may imagine, the shear modulus is very similar to the Young's modulus for tensile, and also the bulk modulus. So let's use the same exact material. Shear of aluminum is equal to 2.5 times 10 to the 10th power Pascal, and the shear modulus for rubber is 0.0002 times 10 to the 10th power Pascal. This is much smaller even than the Young's modulus. Just imagine trying to shear rubber, say some sort of rubber object. It should be easier to shear than to stretch. So now we have a last bit of free space in the middle. What we can cover with the middle is just a general concept here with the stress equals modulus times strain. And this is only applicable within a very small range of the strain in percentage. So let's do a diagram here. So if the stress is the vertical axis and the strain horizontal axis, we'll have this this proportionality for a while. So here's a proportionality for a while, and then it becomes a little less proportional. It just starts to do that, and then it does some interesting thing, and then here it breaks. And within this range, this is the range of proportionality. So this is Hooke's law. This range. And beyond this range, Hooke's law no longer applies. But in most cases, when we're discussing this stress and strain, we're not trying to stretch an object or compress an object beyond Hooke's law. For example, a very common application of the Young's modulus, or even let's use either Young's modulus or the Shear modulus, is to make a digital scale. A digital scale, how do you make that? Well, a digital scale is a piece of aluminum, and they drill the aluminum so that the middle of the aluminum is thinner, much thinner than the two ends that are bulkier. So that thinner parts can be easily compressed, stretched, or you can also shear that, so the center will actually start to bend very, very slightly. You won't be able to see it, but if you place some electrical components on this part that is going to stretch or shear, their resistance will change as you shear them. So that can be amplified and turned into a digital signal, and then you can say weigh an object or weigh yourself on a bathroom scale. And that's all thanks to the Young's modulus or this shear modulus, and we can make it work even when the values are so big. So big, but we know that this area, we can use the area to our advantage, right? We drastically reduce the area, and the force doesn't have to be so big in order to produce a very large outcome on the right side, right? Or not large, but observable by sensitive electronics. Thank you.